Greetings, everybody. Thanks for joining our session. I presume that people are at the other end here. This is the session Adapting Infrastructure to Climate Impacts, 1:45 to 3 p.m. And I am Mikhail, a faculty member of Civil, Environmental, and Sustainable Engineering at Arizona State University. And I've had the pleasure of being joined by two additional folks. One is Dr. Sam Markolf, currently also of Arizona State University, but Sam will soon be transitioning as a faculty member to University of California, Merced. And then we also have Malcom Araos of New York University. So today, before we get in, I first want to sort of set some ground rules, or I should say expectations of what's going to happen, and also give a thank you to our sponsors. So what we're going to do is each speaker today, there are three, myself being the third. So we'll start with Malcom, go to Sam, and then myself. Each speaker is aiming for roughly a 16 to 18-minute presentation, at which point that will leave us time at the end for substantive Q&A discussion. The way that I request that we do that, participants, would be to put your questions in the team chat, in the chat, as you think of them. And I will be, as the moderator, watching those questions. And what I'm going to do is, if I see sort of a clarifying question or sort of a minor question, I'm going to pass that along to the speaker at the end of their talk. But I'm going to save the big questions for the very end, where I will then direct them to one or more of the speakers, again, myself included. So again, minor questions or clarifying questions, just put everything in the chat, but I will direct those right at the end to the speakers. And again, we'll try to facilitate roughly a 20-minute discussion at the end for bigger points, which would give us an opportunity to sort of talk about some of the issues that we've each raised together. That being said, as we roll in here, I'd like to thank our event collaborators. So there's a number of sponsors, and our host, UCLA and team have gone and found some great sponsors here that have made this event possible. So, thank you to them, and want to acknowledge their contribution. I want to kind of remind everybody that, just under some technical interface details here, that there are a number of widgets that you can turn on, turn off, minimize, maximize, those sorts of things. You can resize the window, for example, the presentation window. And, I think you can kind of move things around to make it easier or to emphasize whatever it is that you want to see. With that, let's kick in. So we're going to start with Malcom, then move over to Sam, and then finally myself. And Malcom is a PhD student at NYU and focuses on the area of broadly climate adaptation and public participation, social equity issues. So with that, I'm going to turn it over to Malcom, who's going to give a little bit more on his background and then jump into his presentation.
Yeah, thank you very much, Mikhail. I have to say I'm very humbled to be presenting among such an impressive group of researchers today, including in this session. Okay, so I'll get right into it. So my name is Malcom Araos, and I am a PhD student in sociology at New York University. My presentation today is called Democracy Underwater, and it's about the relationship between public participation and technical expertise in the planning of climate adaptation infrastructure in New York City. So I'm going to tell you a little more about what this presentation is about, and I promise this is the most text you get from me today. So I'm interested in the social dimensions of planning for a climate change future. So from what I can tell, the two other presentations in this session will focus on the technical challenges of design with regards to adapting infrastructure to climate change. But I want to focus on what happens when you combine that technical expertise with input from the public. So how do those two forms of knowledge mix? So you may ask, why should the public participate in climate infrastructure planning? So isn't this a technical, complicated issue? And lay people shouldn't necessarily have a role to play in this. Maybe this is an issue that should be left to climate scientists and engineers and so on. Well, there are some pretty convincing reasons that people have given for why the public should be involved in decisions about climate change infrastructure. The first reason is maybe intuitive to most of us, right? That people should have a voice in the issues that affect their neighborhood. If a huge seawall is coming to your neighborhood, for example, chances are that you feel like it will affect your life, maybe your access to the waterfront, for example, and so that you will want to have a say in how the project is designed. Social scientists sometimes call this procedural justice. They argue that it is just for a community to have input in planning procedures for adaptation projects, especially if that community is a socially vulnerable group or has been a target of historical injustices, such as a low-income community or communities of color, especially in the United States. When citizens have influence over how their neighborhood is planned, the argument goes, the conditions of the neighborhood improve for those residents. The second reason is maybe a little bit more cynical, and this is what the IPCC emphasizes. Scholars also say that residents don't like it when a project is implemented in a top-down manner, when the government or another actor just imposes their plan on the neighborhood. So by being receptive to public input, the project will be seen as like more legitimate in the eyes of the community and will be less likely to spark out resistance. But there's surprisingly little empirical research on how this is done and to what effect in the real world. So what are some real world cases of this being successful or unsuccessful, and why? So I'm interested in this question, right? How do governments implement participatory or technocratic decision-making styles? What are their effects and what obstacles do they face? So how do I go about answering this question? Well, down the street from me where I live, probably the largest and most expensive climate adaptation was beginning to take shape a few years ago when I started grad school. I'm sure this is an image that you've probably seen already today in more than one session. And this is the project to protect Manhattan, the Manhattan coast, from the coastal effects of climate change. So mainly sea level rise and storm surges. So this is a preview for now. I'll give you a lot more details on this, but I studied this planning process for this project for over 2 years. I went to every planning meeting I could, community board meetings, protests, events, and I interviewed activists, planners, engineers, architects, public housing residents, basically anyone who would talk to me about this project and was associated with it. And the story I'm going to tell you today will focus on one aspect of this project. This is an in-depth tale of how things can go pretty wrong. The story is about how this project went from a process that was intensely participatory at the beginning, using the language of radical inclusivity, and had reached a great consensus within the neighborhood, not perfect, but a pretty good consensus, to a project that sidestepped public input completely, started relying on technical expertise of engineers, and eventually at least elicited even lawsuits from local community groups. Okay, so backing up a little bit, as most of you probably know, in October 2012, Hurricane Sandy struck the east coast of the United States. And in New York, 44 people died. The storm caused $33 billion in damages, and flooding caused outages of electricity and heating in many low-lying coastal neighborhoods. Public housing buildings, like the one in this photo on the Lower East Side, flooded at higher rates than market housing. And in some affected areas, the city took like weeks to restore electricity and heating. And across the city, like in any disaster, low-income neighborhoods were disproportionately affected. In the case of Sandy, by flooding and outages to electricity and heating. So if climate scientists are correct, then the current path of emitting carbon into the atmosphere at the same rate as today will take us to about 4 degrees Celsius of warming or more. And this map shows the kinds of sea level rise that we can expect from those levels of warming in New York City. So Sandy triggered a massive policy agenda of resilience in the city, and resilience defined in one particular way. So Mayor Bloomberg at the time defined resilience in the months after Sandy as, as New Yorkers, we cannot abandon our waterfront, we must protect it. So resilience defined as armoring up the New York coastline. This is maybe different to what we've already heard today from Kian Go this morning, notions of resilience from below. And this is also what sociologist Daniel Aldana Cohen calls a logic of a fortress of solitude. So after the years of Sandy, New York committed to a policy agenda of protecting itself from impacts, and efforts to decarbonize during this time were actually sidelined. So this plan, called the Big U, was, I'd say, the most ambitious project to come out in the post-Sandy years. The Big U was born of a process called Rebuild by Design. Rebuild by Design was an initiative from the federal government, from HUD, and the President Obama's Sandy Recovery Task Force. And the goal was to do a design and architectural competition that brought together neighborhood groups, designers, planners, academics, and so on to rebuild after Sandy and plan for future sea level rise. So 10 projects were funded, and I would say that the Big U became the flagship project for resilience in New York City. And lots has been written about the Big U, much of it very critical. I encourage you to read more. And it's become kind of a symbol of a type of climate adaptation planning, which is to armor up the coast, which became the logic of post-Sandy New York City climate policy. And at the heart of the process of developing the Big U were two principles. One was to build a piece of infrastructure that would keep the ocean out of the city, but at the same time that could act as a park, so a green public amenity that would improve people's lives who lived near it. A second principle was that the infrastructure in the park would be designed in conjunction with the people whom it would serve. So a little bit more of this in a second. So the Big U had to go from architectural concept into a real infrastructure project that was to be built. So as it crunched through the federal, state, and local governments, it became a series of smaller projects to be done in phases. The first phase or compartment is the East Side Coastal Resilience Project, which covers this area marked by the white line here and encompasses much of the Lower East Side and East Village. So the LES, the Lower East Side, is one of the most racially and economically diverse neighborhoods in Manhattan. However, this kind of neighborhood level diversity hides what is actually a neighborhood that is highly racially and economically segregated at the block scale. So the LES has 26 public housing developments, accounting for 23% of all rental units. And while the neighborhood has some of the highest rent prices in the city, the rate of people below poverty rate is actually around only 7%. Here in the map in orange, you can see where the public housing is located in the neighborhood. So this part here in green is on the edge of the neighborhood. It's called the East River Park, commissioned by Robert Moses in the 1930s. And this is the part of the neighborhood that would be rebuilt as green infrastructure. So as I said, the project originally took it very seriously, the process of public input. And by all accounts, this is true. Residents of the Lower East Side that were involved in this process recount that it was a very meticulous affair. Designer and planners would call meetings and present designs and ideas and ask questions. Residents would answer questions and provide comments. In this picture, using maybe Post-it notes on a map. Then the designers would come back to the drawing board, and then maybe a month or two later would come back presenting a different new plan. And this is an iterative process that worked to hone in on options that worked for everyone. So I'm not going to go over exactly what this case is, but you get the sense of the design evolving through time based on feedback and discussion among different groups. So this is a very important slide. This is about a cross-section of what the park would look like. And a key part of this image is that the park would flood during a storm surge event. So, but a berm on the inside of the park, you can see the orange kind of stick on the left side of this image, would prevent the rest of the neighborhood from flooding. So according to one designer, participants overwhelmingly chose these green berms on the inside edge of the park, on the left side of the image, that also increased neighborhood access to the water while protecting housing, public housing, and building a natural buffer that would absorb storm surges. And a key feature of this design was the maintenance of existing trees and shrubs in the park. So the use of natural infrastructure for protection as a sponge in the event of a major coastal storm, rather than rebuilding the public amenity entirely. This proposal constituted kind of an intentional departure from typical seawalls. However, this is meant to be an ominous slide. In September 2018, the city presented to the public a completely different project than agreed upon. So this is the difference between the two plans, the before and after. The new plan on the bottom would raise and rebuild the whole park rather than build the flood protection on the left side by the FDR Dryad. So everything currently in the park in the new plan would be destroyed and rebuilt. And city agencies appealed to engineering and maintenance concerns. And at each meeting, technical experts would present the reasons for why the previous plan, the plan of public consensus, was not technically sound. And engineers from the Department of Design and Construction have said that this concrete barrier can't be built there because building the barrier requires closing the highway, which can only be done at night, but then they can't do loud construction work at night. Also said that there's some utility cables under here that can't be moved. Planners in the Parks Department had a slightly different story. They've told me that Parks doesn't have a budget to manage a park that is constantly flooding. The park would flood twice a day by 2100. And they're not on board with this idea of parks as sponges. So the Dutch approach to flood management of quote unquote letting the water in is not something that the city is interested in pursuing in Lower Manhattan. So in a storm situation, this is the difference between the two plans. The previous plan on the left allowed the park to flood and the new one doesn't. So this is an image from LES Ready. I didn't include the attribution here, I should have. So after the change, pretty much all the activists and many residents who had been part of the previous process were now vocally against it. This was manifested through marches and demonstrations like the one pictured here, and eventually lawsuits. And now it's almost 8 years after Sandy, and this project has been paralyzed and delayed for years and still hasn't broken ground. So what were activists and people that rejected the plan now are like angry about? And primarily they felt that their input was actually no longer influencing the project. The city maintained that they were having a participatory process because residents and activists had a chance to voice their opinions at meetings and public hearings, but city officials kept appealing to the technical expertise of engineers as reasons why the opinions of residents couldn't be included in the plan. A second big reason that activists rejected the park was that the new plan would entail destruction of around 1,000 trees. And a third reason is that the park would be closed for around 4 or 5 years of construction. Some local residents are rightfully afraid that they will lose an important piece of public space, especially during a pandemic. A group of activists, park advocates, actually even sued the city. They argued that turning a park into an adaptation infrastructure project means that the park no longer functions as a park, and there's a special legal process the city needs to undertake to destroy parkland. So an interesting thing about activists that reject the project is that they're often older, often white environmental activists with quite progressive personal politics. And these activists have chosen to prioritize kind of short-term conservation of nature in their neighborhood over long-term protection from climate change impacts. And they have even called this adaptation infrastructure project a type of climate change denial because of its destruction of trees, because trees suck carbon out of the air, and because it's prioritized protecting the city rather than decarbonization efforts. I've also had planners tell me that they called this project, that they called the activists rejecting this project also climate change deniers because they would rather protect the trees rather than protect the neighborhood from long-term flooding. So I think this is a really interesting conflict. The last thing that I want to tell you about the story in the Lower East Side has to do with community politics. So the older activists who rejected the city's plan were the most vocal in public hearings and often talked in the language of representing the whole community. And in environmental justice, we talk a lot about frontline communities as a homogeneous group of people facing a common impact. But I want to bring your attention back to this map of the Lower East Side and remind you how much public housing is located in the floodplain. And what I started noticing in public hearings after a few months is that often people living in public housing or tenant association presidents wouldn't talk to the community. They would talk for themselves or for people living in their building. And often they were supportive of the city's plan, even if they found it flawed. So to quote a tenant association president, "We don't care that there's a 4-year park closure. That's a drop in the bucket for 100 years of protection to the 20,000 people who live in public housing in New York City. Nobody speaks for us but us." Okay, so these are my kind of take-home messages. So this presentation that is more oriented towards planners, I'd say, than sociologists. If you want to read the sociology paper, feel free to get in touch and I can send that to you. So first, public participation in adaptation infrastructure is absolutely essential, not only because it's just a good or a just thing, which of course is true. The upshot is that adaptation infrastructure that is more democratic is more likely to be successful. And participation in itself is not sufficient, and people participating in processes need to be able to recognize their own influence on plans, and that city officials' appeals to the rationality of engineering or climate science are not enough to produce legitimacy for plans. So participation needs to be coupled with democratic outcomes. And second, there's some difficulty in assembling a public for public consultation. So frontline communities actually that we talk about in a homogeneous way are actually often heterogeneous neighborhoods, and groups might have conflicting interests. So I think planners have to be careful about how they make decisions about whose voices they seek to prioritize during the process of public participation. Lastly, the last thing I want to say that of course we can't generalize from a case study to predict what will happen in other infrastructure projects in other cities, but I chose to study New York City precisely because it's not representative, but because it's extreme. So it shows that this process or problem in particularly clear relief. So New York City is a city with strong political willingness to respond to climate change, tremendous resources, and an intention to democratize climate planning. And so if New York City can't work out how to do democratic large-scale adaptation infrastructure, we're going to have bigger problems in other places. Okay, thank you so much for listening to me. That's all for me.
Awesome, thank you, Malcolm. As a reminder, I see some folks are using the Q&A feature to provide questions, comments, thoughts, which is highly encouraged, so please continue to do so. If you have questions for Malcolm or any of the other speakers, please put them in there. Malcolm, there's one question in particular that I think would be nice if you could maybe elaborate on at this moment, and that's from Sam Bloch, who says, so what do you think is the most compelling, most likely explanation for why the original urban plan was thrown out? Parks don't want to pay for maintenance of a sponge park, ? City Hall doesn't want to convince taxpayers to pay for that maintenance, ? Or is it indeed the engineering, ? Do you have any thoughts on that?
So this question comes up a lot. So I feel like sociologists can't look into the black box of decision making behind those closed doors. But I think both of those answers come together to make a compelling argument. And the city actually has used either argument in different circumstances. So it's actually hard for the person that's analyzing this, or if you are just a spectator in this debate, to actually identify which exactly is their concern. Either actually true engineering concerns, or is it just that the city doesn't want to pay for maintenance of the park? I think the city's actually been unclear about which exactly is like the bigger priority or the bigger barrier that has led them to change the plan. I know that's always not a great satisfying answer, but it is what's been true, is that the city itself has been ambiguous in their reasoning.
Thanks, Malcolm. Let's switch over to Sam Markolf at this point. There will be more time to ask Malcolm and myself other questions after all the talks are over. So again, I encourage you, please put your questions, comments, thoughts in the Q&A feature, and we'll get to them presuming there's time. So next up is Dr. Sam Markolf, who is an assistant research professor at Arizona State University. Sam and the following talk, which will be by myself, both kind of switch gears into what it means to design infrastructure under climate uncertainty. So I don't want to reduce the comment away, or reduce the complexity away, but basically the questions that Sam and I have been asking, both independently and some together, revolve around this notion that a perspective of everything is going to get worse and we need to overbuild in preparation for that is probably not a well-balanced perspective. So Sam and I have been in various ways tackling the question of, what does it mean for infrastructure to be designed in the future under uncertainty? So with that, I'll hand it over to Sam, and afterwards you'll hear a talk by me on a related topic. So Sam, all yours.
Great, thanks, Mike. Good afternoon, everyone. It's a pleasure to be here. As was just said, I'm Sam Markolf. I'm currently in the Department of Civil, Environmental, and Sustainable Engineering at Arizona State University. And starting in January, I'll be joining the faculty in the Civil and Environmental Engineering Department at University of California, Merced. And today I'm excited to be here and share a little bit about our ongoing work related to the relationship between infrastructure design storm standards and broader resilience efforts, and some of the challenges that kind of emerge within that space. I always like to start off kind of at the highest level and then drill down as I move along. So despite increasing understanding, attention, and efforts to reduce the impacts of climate change and extreme weather events, scenes like the ones depicted here are unfortunately still a regular occurrence. So at the highest level, our motivation is to take a deeper look at the role that infrastructure plays in mitigating or sometimes exacerbating these types of events. And in particular, we take a critical look at design criteria to which infrastructure are built and explore opportunities for adjusting or changing those design criteria in the face of the challenges of the 21st century. I don't want to get too into the weeds, but before progressing any further, I want to make sure we're all kind of starting from roughly the same place. So I think it is useful to just take a moment and discuss design storms and design storm criteria in a little bit more detail. Although they exist for a variety of hazards and infrastructure, design storm criteria are most prevalent in stormwater management and flood control, and often refer to the amount of rainfall within a specified amount of time and within a specified geographic location used to determine the type, size, and location of infrastructure. Design storms for extreme precipitation and stormwater are often expressed in terms of a return period, such as a 10-year or a 100-year event, which is essentially a shorthand for annual probability of a specific event occurring in any given year. So for example, I'm sure many of you have heard these terms used, 100-year storm, 10-year storm used. So for example, the annual probability of a 10-year storm is 1 in 10 or 10%, and the annual probability of a 100-year storm event occurring is 1 in 100 or 1%. Once that return period is chosen, resources based on historical meteorological data, such as Atlas 14, which is produced by the National Oceanic and Atmospheric Administration, or NOAA, can be used to create what are called intensity duration frequency curves, or IDF curves, to determine the amount of rainfall the infrastructure should be built to handle. So for example, the figure and the table on this slide indicate the Atlas 14 values for Phoenix, Arizona. Assuming a return period or frequency of 100 years, the stormwater management infrastructure would need to be able to handle between 0.6 and 3.35 inches. So you can see that kind of on the row, the row labeled 100 for under frequency years. You can see that range of values there. And this range depends on the type of storm for which one is designing. The city of Phoenix itself selects 2 hours as the most suitable storm duration. So its infrastructure must be capable of handling at least 2.6 inches of rainfall within a 2-hour period. So having kind of said all that, why are we talking about design storms and design storm criteria? Well, I guess at the highest level, design storm criteria in one form or another are pervasive across infrastructure types and scales, especially within cities. And as a result, vulnerability to extreme weather events within cities is linked to urban infrastructure systems and their inherent design storm criteria. Therefore, as cities are increasingly faced with climate change, shifting populations, and growing complexity, design storm criteria likely warrant additional scrutiny and even possible reimagining as key mechanisms for achieving desirable resilience and adaptation outcomes in the coming decades. So to that end, our work explores the history and evolution of design storm criteria, compares design storm criteria across different infrastructure systems and hazards, identifies some of the major challenges currently facing design storm criteria, and finally proposes some potential next steps for facing these challenges. And in the remainder of the presentation, I'll kind of walk through each of these 4 key bullet points in more detail. starting with the kind of history and evolution of design storm criteria. So given the long-lasting nature of many infrastructure systems, decisions and design practices made several decades ago can influence cities and infrastructure systems in present day. Therefore, a historical examination of our infrastructure systems can provide some valuable insights into how current dynamics and performance, or again, lack thereof, came to be, and also help us think more critically about where things may be heading in the future. Depicted here is an abridged timeline of key events in the development of flood control standards at the federal level. Unfortunately, we do not have time to go into much detail on these events, but there are a few key takeaways that I'd like to highlight. First, the 100-year event has a long track record of being the most widely accepted and adopted standard. However, despite our best efforts, it was difficult to determine what criteria, if any, were used to support its initial recommendation in the 1960s. So in other words, it is still a little unclear how the federal government originally came to advocate for the 100-year storm event as a standard, as opposed to, say, using a 50-year storm event or a 200-year storm event or a 500-year storm event. There's a little bit of uncertainty there. Second, the National Flood Insurance Program and similar programs and endeavors has facilitated the adoption of similar criteria and practices at the state and local level. Therefore, although states and municipalities can and do establish their own design storm criteria, they often do not deviate much, if at all, from the standards and practices established by the federal government. And finally, and perhaps most importantly, most of the key events in the development and evolution of design storm criteria occurred in time periods where the dynamics and effects of climate change were not really a big thing. They weren't really clearly understood or considered or discussed widely. And this is a key point that we'll return to later in the presentation. Sorry, it looks like on my end, this one isn't showing up very well, but nonetheless, one final observation from our historical analysis is that design storm criteria tend to always align with what's called frequency-based design, where the design is based primarily on a prescribed recurrence interval. So again, that 100-year storm event, and the consequences of a system failure are not explicitly considered in the design. However, given advances in computing, data collection and availability, and modeling capabilities, now appear to be at the point where a more risk-based design approach, where failure and the impacts of failure are explicitly considered in the design, are possible, and I'd even argue more appropriate. And we'll return to this point again later in the presentation. So in addition to reviewing the historical aspects of design storm criteria, we also wanted to get a snapshot of the current state of design storm criteria. And to do so, we conducted a case examination of various infrastructure systems and their specific design standards within the Phoenix metropolitan area. The table depicted here includes 3 different infrastructure sectors, including flood control or stormwater management, electrical power generation, and on-road transportation, as well as 3 hazards: precipitation, temperature, and wind. For each combination of infrastructure and hazard, we examine whether design criteria appears to exist, the specific values of the design criteria if it exists, and whether the criteria aligns more with the return period approach or a threshold approach. And I'll explain these in a little bit detail in just a second. Overall, wind was the hazard with the fewest related design criteria. Precipitation related design criteria was based on return periods, where it has a temporal or probabilistic element, while temperature and wind based criteria were based on intensity thresholds. Finally, the absence of any temperature-related design criteria for flood control infrastructure appears to be an issue that warrants further examination. In particular, there's a growing body of research that links extreme temperatures with water system disruptions through things like pipe ruptures and pump failures. And so the lack of any type of design criteria related to temperature may be increasingly problematic and therefore worthy of additional attention in the future. So kind of given that broad overview of how we've gotten to where we are now and where things currently stand, we can turn our attention to some of the major challenges that we've identified facing this approach moving forward. First, we have climate change and climate non-stationarity. So returning to a point introduced earlier, many design standards, criteria, and practices are predicated on the idea of stationarity, where the properties of a system do not change over time. However, due to climate change, as well as a host of other factors like population and demographic shifts, we appear to be entering a period of non-stationarity. So in essence, the past may no longer be a reliable predictor or indicator of the future, and infrastructure systems may be entering a period where they are designed for conditions that no longer persist. For example, a 2018 study by Lopez and Samaras found that by the year 2050, projected changes in precipitation patterns due to climate change will stress stormwater infrastructure beyond their design capacity in at least 43 US states. And I believe Dr. Chester will speak to this in his presentation, but it should be noted that although it frequently appears to be the case, climate non-stationarity does not necessarily mean that infrastructure will always be under-designed for future conditions. There may be cases where infrastructure gradually becomes over-designed as extreme events become less intense or less frequent as a result of climate change. So in particular, some areas are expected to become more drier over time. And in those cases, the infrastructure may actually start becoming over-designed for what the future conditions might be expected to be. And so ultimately, the non-stationarity conditions presented by climate change may undermine the data upon which much of the quantitative understanding and management of infrastructure risk is based. Therefore, design criteria based on historical return periods and past data will likely become less reliable. In their stead, efforts should be made to develop and implement design standards that are increasingly forward-looking and capable of handling conditions of non-stationarity. The second major challenge that we're starting to see is increasing complexity and interconnectedness within our urban systems. So in addition to the issues presented by climate non-stationarity, increasing complexity within and among urban and infrastructure systems is another major challenge confronting current design and implementation paradigms. Not only are urban and infrastructure systems comprised of many integrated components, users, and managers, they are also interconnected to other social, ecological, and technological systems. And the conditions and context in which infrastructures exist begin changing almost immediately upon their installation and continue to change and evolve throughout their lifespan. A good illustration of this is the recent floodings and issues that we've been seeing in Houston, Texas over the past decade or more. These flooding events were likely exacerbated by lack of strict zoning laws in the area, rapid population growth, and urban sprawl over the past several decades. So although climate is certainly a major factor in this, there's also these other kind of social, economic, and social ecological issues going on. So in particular, since the construction of two of the region's primary flood control mechanisms, the Addicks and Baker reservoirs in the 1940s, much of the population growth and development and the decrease in impervious surface that comes along with that has occurred in suburban areas upstream of the reservoirs, which has in turn drastically altered the hydrological conditions for which the reservoirs were initially designed. Elements of this phenomenon are depicted on the slide, where satellite images depict the growth and development that occurred around the Baker Reservoir between 1984 and 2016, and you can really start to see the rapid growth in development and decreased impervious surfaces that occur over this time period. And so ultimately, increasing complexity within and across urban and infrastructure systems makes it exceedingly challenging to fully implement any form of risk analysis or management. Any distinct causal relationships within interconnected systems become increasingly difficult to discern. The likelihood and potential consequences of a disruption become increasingly unknowable and unpredictable. Therefore, it appears that grappling with complexity will become increasingly necessary if we are eventually to move from a frequency-based design standard or approach towards a more truly risk-based one in which we are able to more completely account for the failures or disruptions. The third major challenge relates to the phenomenon of concurrent hazards and propagation of failures, which again is kind of related to the interconnectedness of these urban systems. And in particular, the fact that infrastructure systems are increasingly subjected to concurrent hazards and the propagation of failures due to these interconnections. However, the emphasis on a specific design storm or a specific infrastructure may result in the unwitting underappreciation of these conditions. So for example, in 2014, there was some major flooding on Interstate 10 in Phoenix that occurred not as a result of under-designed or failure in the stormwater infrastructure itself, but as a result of power outages in some of the pumping stations along the highway. And although we don't have time to discuss the figure in great detail, it further illustrates some of these issues. In particular, the figure outlines different pathways of disruption from extreme heat that can propagate from one infrastructure system to another. And in particular, it shows how the electric system, the information communication system, and the water system can all lead to disruptions in the transportation system under various circumstances and scenarios. And so ultimately, there appears to be an opportunity and need to better understand which hazards may occur simultaneously or propagate from other systems and incorporate these dynamics into infrastructure design. And in doing so, greater coordination and collaboration across infrastructure systems and managers could prove to be very beneficial. And then finally, design storm criteria can contribute to various forms of what we call maladaptation, which can be defined as actions taken to reduce vulnerability in one context that ultimately increase vulnerability or adverse effects in other contexts or amongst other groups. For example, design storm criteria appear to mostly align with the resistance to disturbance or returning to normalcy perspective. However, this approach appears to be increasingly misaligned with emerging thinking that frames resilience as a dynamic and iterative process that emphasizes the ability to transform, change, and adapt in the face of continual and sometimes surprising stresses and strains. Design storm criteria can also contribute to maladaptive outcomes in governance. In particular, there is evidence that calculative practices such as design storm criteria can contribute to the mischaracterization or overestimation of the level of certainty and stability present in increasingly complex and uncertain environments. Similarly, the actual or perceived certainty derived from calculative practices may contribute to the perception that new or innovative ideas, policies, strategies, and transformations may introduce unnecessary uncertainty or avoidable risk to the system, thereby crystallizing the system in a potentially maladaptive state. And we kind of just heard an example of this in our previous presentation. And finally, the knowledge, skill sets, data, information, and financial resources required to conduct and interpret calculative practices can result in inequitable power dynamics and outcomes amongst different groups, systems, and perspectives. For example, community members who are not well-funded or not well-versed in calculative practices may have difficulty engaging in productive discourse, discussion, and negotiation of specific resilience policies and practices, Likewise, more qualitative objectives such as quality of life or walkability, or novel but uncertain approaches such as nature-based solutions or safe to fail may be overlooked or de-emphasized because they do not align as well with the parameters of a particular calculative practice or viewpoints of the institutions conducting the analysis. So with those challenges in mind, I will wrap up my talk by proposing some possible next steps and ways we might be able to move forward with this knowledge. So despite the challenges and issues described throughout this presentation, design storm criteria have provided a lot of benefit and are likely to remain a fundamental component of infrastructure development and implementation for many years to come. However, considering that there are limits to how much infrastructure systems can be expanded or enhanced, we posit that fundamental shifts may be warranted in how we think about risk in the design and implementation of our infrastructure systems. So at the scale of a single component or subsystems, frequency-based design similar to what we currently have may continue to be effective. But at the system scale, there is an opportunity and probably even a need to more explicitly consider incorporating failure consequences into infrastructure design and management processes. Instead of relying on design criteria that are relatively static, we also need to strive to find ways to incorporate capabilities of experimentation or continual refinement to adapt for the new normals that we're expected to experience due to climate change, increased complexity, and the recognition of maladaptation. And so overall, we view the issues and challenges outlined here as a starting place for much of the research, analysis, discussion, and collaboration that still need to happen. And as these efforts progress, design storm criteria and infrastructure resilience practices can continue to evolve in a manner that increasingly weighs the broad impacts of actions or inactions across all members of society and is conducted in a manner that is as open, transparent, and inclusive as possible. Thank you all very much for your time and attendance today, and I look forward to suggestions, questions, and broader discussion. Thank you.
Excellent. Thank you so much, Sam. There's a number of great questions that have come in, and in the interest of time, since there's 30 minutes left, I think that there's going to be some overlap in those questions between Sam and me, given that we're talking about somewhat similar topics. Also, I see that a few additional questions came in from Malcolm. So why don't I suggest that I'm going to jump right into my presentation, try to be done in 15 to 20 minutes, leaving about 10 minutes for Q&A at the end, at which point I'll go back and Sam, I'll give you a few of the questions that popped up, and you know, Malcolm, I'll reintroduce some questions for you. So
great.
Thank you all again for your attention so far, and I'm gonna sort of build on a little bit what Sam has been talking about. So I'm gonna talk about this question: are infrastructure under-designed for climate change? And the reason I bring up this question is not to be a climate contrarian, so to speak, but instead to introduce the reality that is the complexity involved in understanding whether or not our infrastructure are over-designed, okay? And you'll get a sense of what that means in the next few minutes. So I wanna give you guys, start with a story, okay? And I'll do this quickly, but the story goes that, you know, imagine a road outside of your house or outside of your building or in your town nearby, however you can imagine. That road was constructed around 1950. That road is still there, right? A lot of the original infrastructure underneath it might still be there, the subbase, maybe, you know, some of the water lines, but let's imagine the stormwater pipe underneath that road in particular. That stormwater pipe was actually sized when the road was built. It was sized in 1950. And in 1950, let me give you a little context. What did we know about how intense environmental conditions were? So Sam was talking about the 100-year event or the 50-year event or the 10-year event that corresponds to so much water that's dropped on that location, right? So in 1950, what did we know about stormwater intensity or precipitation intensity? The answer is almost nothing, very little, actually. Why? Because where do these data, where does this information come from? Right? It comes from sensor networks, weather stations, precipitation gauges, right, that are all over cities. And in 1950, we were at the infancy of these stormwater gauges or rain gauges, okay? So let's imagine this road in 1950 that's being constructed and somebody says, I need to put a stormwater pipe under the road. How big should I put it? How many inches diameter should I make it? And they go to what fledgling information they had about how much precipitation fell with certain intensities. And they did the best they could to say, you know what, it should be 6 inches or it should be 8 inches wide. That should accommodate, you know, a 10-year event. Almost never do we design for 100-year events at a local level. It's always much, much, much lower. So now, fast forward a little bit further into the future, say 10, 20 years, where we've collected an additional 10 or 20 years worth of information. And now we see that the fledgling data from 1950 was actually a point in the actual distribution that was quite high, that actual rain intensity was far lower after we look at the whole data set, the distribution, so to speak, than we thought it was going to be, which means that the asset under the ground, the pipe, is over-designed, and we might never know it, right? And the question then becomes, if you introduce climate change into the equation, and you say things are going to get worse, okay, well, now you've over-designed something under the road, and things are going to get worse. Is it appropriately sized? Versus, what if it's over-designed under the road and things are going to get better? Is it over-designed? The answer is yes in that scenario, right? And this is what I would call the confluence of past and future uncertainties. So it's important that we wrap our head around these issues because we've got almost no money to rehabilitate infrastructure, right? We know the narrative, infrastructure is in disrepair, right? Getting it up to where it needs to be today, let alone for the future, right, is a monumental challenge, right? So we've been tackling some of these questions. How do we surgically invest? Think about strategically where to place resources, given the massive scale of assets that are out there that we need to adapt, so to speak, to climate change, right? And these are the colleagues that I've been working on with these questions. So, you know, infrastructure rigid, that's the heart of the problem, okay? We can't forget this, that if infrastructure were agile and flexible and climate was making the environment move faster and faster, it might be less of an issue because we could basically say from year to year, every 5 years to 5 years, you know, okay, it's insufficient, let's change that asset and make it different, right? The problem is fundamentally that the cycle times of infrastructure are far, far, far slower than the cycle times of the climate nowadays, as Sam was referring to non-stationarity, okay? So there's a mismatch in how fast things are moving, right? Our human-built systems are designed intentionally to move for good reason, very, very slowly. But now the environment is moving faster and faster. That's the fundamental problem that we're dealing with. We predominantly emphasize what is called robustness as our strategy to resilience or climate adaptation when it comes to infrastructure, okay? We generally fall back to the tools that we have been taught. I am very much to blame for that as an engineering instructor at a university. We very much teach how to make things tougher, stronger, armoring, strengthening, to hold back the environment. That's been our goal for about 100 years now. The problem, as Sam points out, is uncertainty, right? So if I say, but it could get way, way, way worse, and we can't quite design to that, or to design to how bad we think it could get, we don't have the money. We don't have the resources. We don't want that massive, massive levee in our backyard, right? There's many ways in which we could limit what robustness can do for us, right? But going forward, we think in general, in the infrastructure community and in the resilient infrastructure community around a much broader set of what are called resilience regimes. These come from Dave Woods at Ohio State, where, you know, we do 1 and 2 already, but, you know, can we think a little bit about what it means to extend the capability of a system, you know, when the primary system fails, right? If the water distribution system fails, can we make sure that people have drinking water on their shelves? In California, you do a very good job of that with with earthquakes and making it clear that, you need so many gallons of water per person for so many days, presuming the big one is going to hit, right? But can we think more broadly across infrastructure about how we extend the capability of infrastructure in the face of surprise, right? And then this idea, as I mentioned, of sustained adaptability. What does long-term adaptation of our systems mean? Not just let's emphasize what we've had already and think about how to make it survive through, radical cycling of climate, right? Those are very different problems to deal with. Sam showed a chart of this, but I'm going to zoom in on the Luskin Center there at UCLA campus, where I actually looked up the 100-year return event, which corresponds to about 8.36 inches with a plus or minus on it. Notice it could be a little bit bigger, it could be a little bit smaller with a 90% confidence interval, right? That's the reality of what you have to deal with, the uncertainty, so to speak. And, this is how we do things, right? If you're going to build something, in a particular location, you go to a NOAA Atlas, it's currently number 14, and you look up for your latitude, longitude, how intense that precipitation event, so to speak, or in this particular case, it's going to be. And by the way, infrastructure designed around a multitude of environmental hazards, not just precip, right? We might think about heat. In many coastal areas, hurricane-prone regions, wind is actually what's going to dominate how intensely we build something. It's not necessarily going to be precipitation. In Phoenix, it's going to be heat. In some places, it's going to be cold, right? So the environmental conditions are literally baked into the design of infrastructure. We can't forget this. And they're changing, okay? So, here is for Phoenix, a 100-year event. Look on the y-axis, move it over. Historical is red, future is black. And what you can see that what was a 70 millimeter per day, 24-hour precipitation event that corresponded to a 100-year return period is now going to be roughly a 90 millimeter, right? So from 70 to 90, that's what we're talking about. However, you can see that there's large uncertainty swaths with these figures. And these figures don't always cleanly just go up, okay? So let's talk about that for a second. In 1973, the first NOAA Atlas series was released. And actually, a lot of the infrastructure in the United States was already built by 1973, particularly major infrastructure like highways, for example, or interstates. But, of course, we've kept building. In 2003, NOAA Atlas 14 came out. So here's some Western states. Yellow is where things get worse. Red is where things get better, comparing NOAA Atlas 2 to NOAA Atlas 14, okay? So the idea that today everything is worse because of climate change than in the past is not quite consistent. That narrative is not quite there. Actually, as our understanding of where things are better and where things are worse have improved, right? We can see that as we've gathered more data, there's places where we think, we've seen things get worse in terms of, what a 100-year event is, and places where things have gotten better, right? So that's just the present day situation. We took this information and we overlaid it over the US interstate system, okay? And we said, let's look at every single watershed that the interstate system moves through. And let's find when it was designed and what conditions it was designed to, and what that's going to mean as we look forward into the future under climate change. And you may see where I'm going with this. There are certain places where you've designed infrastructure where things have gotten better relative to your RCP 4.5 future scenario, and places where things are worse. I'll put that another way. There's places where relative to climate change and how we already have designed infrastructure, there are assets that are over-designed and there are assets that are under-designed. Okay, that's part of the complexity here. So what does that mean for us going forward? The reality is that we have to come to terms with this past uncertainty in how we've designed things, where infrastructure stands today relative to that past uncertainty, and what that means for the future. And hopefully when I've described this to you, you've said, this is a much more wicked problem than how I've been thinking about it, and indeed it is. But I'm gonna make the case that we have to come to terms with dealing with this under-designed past-future climate uncertainty issue to target our investments of what we prioritize, because we simply don't have enough money to change everything in the system, nor would it make total sense to do that. Okay, so how do we do that? Let's start by looking at a couple domains of this uncertainty. So let's start by looking at future uncertainty and past uncertainty. Okay, so let's look at the y-axis. So here you've got past conditions at the top are less severe than what we've designed infrastructure to. On the bottom, past conditions are more severe than what we designed infrastructure to, okay? So it's 2 dimensions. But then we can add future, that's the x-axis, right? And we can look at the 4 quadrants. So in the future, climate change might be more severe relative to future conditions. And by the way, there are many places, I just showed you some, where climate change may be less severe than future conditions. By the way, if you look at precipitation forecast for California, there's places where the 100-year event gets worse, there's places where the 100-year event gets less severe, okay? So that's what the x-axis is capturing. Okay, so now let's look at those 4 quadrants. What do those 4 quadrants mean? Can you advance the slide? So first, the easy one. In the bottom right, you've got infrastructure in what we've called the severe domain have experienced conditions beyond their design envelopes. Okay, so this is where we essentially designed infrastructure, we under-designed infrastructure. Things are already, or the reality was that things were worse than what we thought they should be in the past. And now climate change is expected to get worse. In this case, we're saying this is the worst of the worst, right? Infrastructure are under-designed currently, things are gonna get worse. That's what you need to prioritize, what shows in the severe domain, okay? But then we can juxtapose that with the other scenario where we call it the guarded domain. Infrastructure can experience conditions far less worse than, or far less than what we thought they were going to experience, right? So, you know, in 1950, we thought it was going to be bad, but it just wasn't that bad. So we over-designed it, right? And now we see the climate forecast actually says things are going to get better in that location, right? We might call that, you know, we're not going to say let your guard down, but we're going to say that's the guarded domain, right? So that's probably your lowest priority. That's where things are over-designed for the future, okay? Now the really tough ones become the other 2 quadrants, because that's where things are moving in the directions that we can't quite make sense of. So we call these the elevated domains. So here, top right, for example, infrastructure have experienced conditions less severe than what they were designed for, but climate change is expected to increase the severity of these conditions, right? So it's not clear whether the balance of these 2 forces results in sufficiently robust infrastructure. And likewise, the bottom left, infrastructure have experienced conditions more severe than what they were designed for, but climate change is expected to decrease the severity of these conditions, okay? So, you know, these are areas where we say we don't have enough information, but we need to be elevated in our concern or maybe in our prioritization of you know, doing something about those particular locations, okay? So this is the reconciliation of past and future uncertainty. And what we advocate for is, you know, given limited resources and given that with those limited resources, we probably need to make pointed or surgical investments, we might want to follow a strategy where we try to reconcile, again, this past and future uncertainty and go down the list, starting with what's most severe, then to the elevated domains, following the guarded domains, okay? So what do we do under deep uncertainty, right? So Sam already alluded to a number of these potential strategies, right? The real challenge, again, is that we are designing systems under assumptions of stability and the environment has become unstable. The basic models that we have, mental and code-wise, that we use to design infrastructure are becoming increasingly irrelevant, right? So we want to just say, look, climate change is going to change the environment, therefore we just need to change our design codes. It's not going to be as simple as that, because climate change has fundamentally or will fundamentally introduce uncertainty or non-stationarity, which is going to undermine our assumptions about stability and how we design, right? So we talk a lot about, and we do a lot of work around the concept of decision-making under deep uncertainty. Robust decision-making falls under that. So this is the idea of how do you minimize regret in your decision-making? How do you leverage social and ecological capacities So to Malcolm, maybe, some of what Malcolm was talking about, right? So if infrastructure are possibly going to fail more, that's safe to fail. I'll come to that in a second, right? How do you leverage the sort of social capacity, social capabilities of communities, right, to be able to respond to that? Instead of simply, saying we're going to hold back the environment so it never happens, right? More broadly, we need to think holistically about across socio-ecological, technological systems. How do we use green infrastructure, for example, to attenuate the effects of these extremes, right? Biomimicry, I think, is a great candidate. And then, we talk a lot about safe to fail in my research group. So this idea that, again, the mental models around infrastructure are fail-safe. We never allow them to fail. And when they fail, they become somebody else's problem, right? Like FEMA. How about the idea that it's inevitable that infrastructure are going to fail? It's inevitable under climate change because we simply can't rehabilitate all of them fast enough and we don't know what we should rehabilitate them to under climate uncertainty, right? So failure is inevitable. So this idea that we should recognize that failure is going to happen, however, we should manage the consequences of that failure proactively, right? Either in design or in preparing for that failure, right? No loss of life is acceptable. But, right, we can think creatively about what it means for infrastructure to fail. So, for example, Room for the River in the Netherlands, where they allow the river to come in instead of holding it back. It floods out farmers. They reimburse the farmers for their crops when those crops are lost. And the reimbursing of the farmers is far less than building giant levees to the maximum or, high end of climate uncertainty scenarios. So with that, lots of background reading here. You guys have the slides. Happy to talk more about that by email or otherwise. Thank you for your attention. And we now have 9 minutes left. So I see a few more questions have come in or comments. And what I'm going to do instead of monopolizing the rest of the time myself is start sending some of those questions over to Sam and Malcolm. Sam hasn't had an opportunity yet. So Sam, let me start with you. And let's see. So, Sam, you got a message from Kai. Are there issues with infrastructure, that is stormwater management systems, for example, that is going to become over-designed in locations where it is going to get hotter and drier, maybe increasing maintenance costs, changing water quality issues, ?
Yeah, I think that's a good question. And I think Mike's presentation kind of spoke to that as well. And so I would say the short answer is yes. And we have a pretty good idea about where those locations are going to be. I guess the general rule of thumb is, dry areas are expected to get drier, wet areas are expected to get wetter. So you can start to see this potential divergence where some areas, the infrastructure is in good shape or over-designed, kind of as Mike was just speaking to, and other places where it is quickly under-designed or was already under-designed. So yeah, I think that's very much the case. And then when that occurs, I don't know if there's much that we really need to do if it ends up becoming drastically over-designed. At the extreme end, you could, I guess, look at it like, it's not a quite apples to apples comparison, but like what's kind of gone on in like Detroit or some places or Milwaukee, where the population that the infrastructure was built to accommodate is no longer there. And now they're having to pay to maintain this major system. And so, yeah, that certainly is a big point of like, yeah, how do we maintain these larger systems that are over designed? And I don't have a great answer for that, but I guess that kind of, again, highlights the importance of, we can't just think like climate is an important piece of this, the engineering elements are an important piece of this, but we also need to do a better job of including these kind of social and ecological factors in as well as we can continue to revise and evolve our design storm criteria. And Mike or Malcolm, I don't know if you have anything you want to add to that.
There's lots I could add to that, Sam, but I'm gonna hold back a little bit. I see a number of really interesting questions that have come up that I'm spinning my wheels on. Let me kick one over to Malcolm. So Malcolm, you got a few additional questions in the Q&A, a few good ones, but let me start with from Veronica. Do you think it's useful to survey citizens about the RBD and later planning processes in order to gather their perceptions of accessibility, traceability, and quality of dialogue?
So I will always say yes to this question as someone that works in this field. Obviously, I believe that more research into like the precise processes of public participation and participatory democracy would be great. Surveys is one way of doing it. You could study the quality of participation and the quality of deliberation and participatory forums in many different ways. You could do quantitative text analyses, something that some researchers are looking into now. Yeah, surveys is one way. Ethnography, interviews are other ways of doing it. The question was also about whether to do it for the RBD process. I would say that kind of stuff already has been done for this rebuild by design process. And so there are many other, like as we had talked about a little bit before, it's a little bit maybe becoming an overstudied project, and I'm partly guilty of that. And so there's many, many different projects that are going on around the world that are using participatory methods, and research into those would be really interesting. And if I can have one like meta comment on this session, I found it really, really interesting to have these really different perspectives, right? And to learn from you two about the technical challenges to engineering for this changed climate, and then kind of downstream, my concerns are like what happens when you start to put those projects into practice. And one thing I would say is that it's so fascinating. You know, there's one really touching question in the comments from Jennifer Bravo about, aren't there other issues with this old way of doing things to keep nature at bay than just uncertainty? And I think climate change, you know, as we've shown today in this presentation, has kind of brought new challenges and new questions for every discipline, right? From sociology to engineering. You know, the infrastructure that was designed for mid-20th century assumption of a stable climate is not something that we can assume right now. And so the discipline of engineering has to change to meet that challenge, and so does the discipline of sociology, which so far is largely not engaged with these issues of climate change. So I found it really, really interesting to hear from the engineering camp today.
Yeah, so Malcolm, thanks for bringing that up. Jennifer, you have a nice comment. You know, uncertainty is just one aspect of rethinking the relationship of humans and nature, and I agree. You know, I think that you know, we in some ways need to be careful in how we frame kind of engineering versus fill in the blank. You know, engineering is very much a social construct. What we do in engineering is the hammer at the end of the arm, and the arm is a social construct of, you know, kind of what we were emphasizing at the time, what we understood, how we structured institutions to deliver services, right? What our thinking was around the relationship between humans and the environment. And, you know, what we're seeing is I would argue, a global fundamental re-challenging of that relationship, right? And I think that, you know, we could talk about this forever, but, you know, I think that has to do with a number of things, not just climate. I think, you know, we have this heavy focus on climate, rightfully so, but, you know, many Earth systems are now wholly affected by human beings. Hydrology, you know, independent of climate, nutrient systems, you know, many of our global natural systems are more and more controlled by the hyperkeystone species, those being humans, right? So, you know, now we enter into an era that we would describe as the Anthropocene, where you see destabilization on global scales, right? So you see destabilization when it comes to climate. You see destabilization when it comes to technology, in the sense that technology is moving faster and faster and faster, right? And we can't begin to wrap our heads around what technology will mean in the coming decades, if not 100 years, artificial intelligence mediating our relationship with the environment. Lots of other kind of dynamics at play, right? Ideological extremism, right? There just seems to be this sort of destabilizing nature to the planet that I think is giving us pause, us in the sort of adaptation, resilience, urban systems community, and saying, you know, what is going on here? And I would argue that what is going on fundamentally is that our systems at the nexus of humans, natural environment, and the technologies we use have become so complex that we are looking for new ways of thinking about that complexity. I think we are really taking a step back and saying, you know, we didn't do things, you know, or we've done things a certain way for a long time, you know, largely based on kind of industrial era thinking. how do we rethink, what is happening and what we need to be doing as a global society going forward? And I think that dialogue is very much permeating, again, the resilience communities, the infrastructure communities, the climate communities, many communities, at least on the academic research side, and I would say even a little bit further than that. With that, folks, I think we are at time. There's breakout 4, rooms 1, 2, 3, and 4 are here. So I'll give you a second to make sense of them. I want to thank Malcom and Sam, for their talks. As Malcolm said, it's great to have these sort of different perspectives, but more importantly, to think about where they overlap and what they mean next to each other. I think that's really, really fun to do, and really necessary to do. And again, thank you, audience, for being here, for being interested, for your awesome questions. I think all of the presenters would be happy to receive follow-ups, I would venture to say. So please email us or get in touch with us however you see fit. So thank you again. And thanks UCLA for organizing this.